In the tutorial video, for example, one of the stress analysis series, we will analyze a beam subjected to mechanical loads. This analysis demonstrates a stress analysis of a rectangular beam fixed at one end, with a distributed load applied to its tip, showing the resulting deformation. A new project is created first. Create a new project. Click the File tab and select New Project. Set up the analysis space as follows. Set Model Unit Meter. Set Analysis Space 3D. Click OK button. The initial setting has been done. Create the model. On the Model tab, click Solid and select Box Specify Length on the submenu. In the Parameter Input dialog box, enter starting point X0, Y0, Z0, and click Next button. Set the width. Enter width 0.2 and click Next button. Set the depth. Enter depth 0.5 and click Next button. Set the height. Enter the height 0.1 and click Complete button. Click Exit button and exit from the dialog box. The box for the beam has been created. We set the analysis conditions. On the Model tab, click Analysis Condition. The Analysis Condition Setting dialog will show up. Select Stress Analysis Galileo on the Solver tab. Click the Stress Analysis tab. Confirm that analysis type is set to Static Analysis and click OK button and exit. The analysis conditions have been set. We assign names to the body attributes and the material properties. Highlight and select the box body. On the right-click menu, select Body Attribute/Material Property. In the Body Attribute/Material Property setting dialog box, enter body attribute name beam. Select 03_resin on Material DB and select 002_polycarbonate PC. Then click OK button in the Body Attribute/Material Property setting dialog box and exit. We set the boundary conditions. On the Model tab, click Select Face on the drop-down list at Switch Object. Or click Change to Select Face button on the left side of Model window. Highlight the left side face of the box and click to select. On the right-click menu, select Boundary Condition. In the Boundary Condition dialog box, enter Boundary Condition name, Fix, and click Edit Data. Select Boundary Condition Type, Displacement. Select UX, UY, UZ, and confirm that UX 0, UY 0, UZ 0 are entered. And click OK button. Then click OK button to exit the Boundary Condition dialog box. Next, highlight the right side face of the box and click to select. On the right-click menu, select Boundary Condition. In the Boundary Condition dialog box, enter Boundary Condition name, Load, and click Edit Data. Select Boundary Condition Type, Distributed Face Load. Set the Z component to -49 and change the unit to KN/M superscript 2. And click OK button. Then click OK button to exit the Boundary Condition dialog box. The boundary conditions have been set. Set the mesh size. On the Model tab, click Analysis Condition. The Analysis Condition Setting dialog box will show up. Click the Mesh tab. Deselect Set the General Mesh Size automatically. Enter 0.05 in General Mesh Size. Click OK button. Run the Mesher in Solver and review the results. Once the analysis is complete, the field results will be displayed. Let's take a look at the gradation contour of the displacement. In the Display group of the Results tab, click Gradation Contour and Displacement Outline. The gradation contour diagram of the displacement will be shown. It can be seen that the z displacement of the cantilever beam increases toward the tip. Next, on the Model tab, in the Display group, change Displacement to Stress and click Element Vector. The stress vector plot will be displayed. By changing the view to right view, it can be seen that tensile stress is generated in the upper half of the cantilever beam's fixed end, while compressive stress is generated in the lower half. Also, click Table in the Show Results group to redisplay the results table. If you check the External/Reactive tab in the results table, you can see that, for the fixed boundary condition, a total reaction force of 980 N is generated in the positive z-axis direction. And for the load boundary condition, a total external force of 980 N is applied in the negative z-axis direction. Be sure to save your project when saving the analysis results. That concludes this video. Thank you for watching.